Hello, BISC130. This is the beginning of recorded lecture 1-2. Getting started on chapter 2, the chemical foundation of life. So kind of like the first chapter, this is another groundwork chapter. I expect that if you've taken any chemistry class in high school, or if you're taking a chemistry class at Tech, that you know all this stuff already, but there are technically no prerequisites for my class BISC130, so we got to go through all this just to get everyone on sort of a baseline of understanding. So a lot of key terms in this chapter, just like the last one, but yeah, it's what these foundational chapters are kind of like. So let's start with some real simple stuff and define matter. So yeah, straight off the bat, key terms. Matter is, reading from the key terms now, anything that has mass and occupies space. So yep, that includes atoms and all the stuff smaller than atoms, which we'll talk about soon. Yeah, all these things are matter. Another important term here is elements. So yeah, I referenced mentioned the periodic table last time. Yep, do not memorize this in any way, but these are all different flavors of atoms that we call elements. Elements are just different types of atoms. I can read the definition of elements. The key terms definition of element is one of 118 unique substances. Each element has unique properties and a specified number of protons. More on protons soon enough. But yeah, elements, just different types of atoms. And you can diagram all these in the periodic table, which the key term just says is an organizational table showing these different elements and their numbers and key information about them. So let's talk more about these building blocks of atoms, the components of an atom. So there are three important components to any atom: protons in this diagram in blue, neutrons in this diagram in red, and electrons in this diagram in green. There are several different ways to draw an atom. This kind of diagram that shows the electrons sort of whizzing around this central area, the central nucleus of the atom, is probably the most accurate way to draw what this looks like. However, if we're counting protons and electrons and stuff like that and trying to see things clearly, this is less accurate, but this is probably the most common way of drawing an atom, where you can clearly see the protons, neutrons, and then be able to count those electrons. So let's start by talking about protons. We can see here there's a big old plus sign on these blue protons here. They are positively electrically charged, and they reside in this center part of the atom called the nucleus, or atomic nucleus. Let's run down some of these stats. Positively charged in the atomic nucleus, mass of 1. So AMU is atomic mass units. It's just a unit for describing the mass of really small things, like the components of an atom. Protons, they got a mass of 1. So, these are their properties, but what does the proton actually do? Well, the protons define how an atom behaves. Hydrogen is hydrogen and does hydrogen things because it has 1 proton. That's the number in the corner up here. If it had 7 protons, it wouldn't be hydrogen anymore. It would be nitrogen, and it would behave like nitrogen, and it would do all the nitrogen things. So yeah, the number of protons is incredibly important. It defines which element a given atom is. Number of protons defines an atom's elemental properties and its atomic number. That's the number you see in the top left-hand corner in a periodic table. So very important. Another component here I want to talk about, continuing on with the nucleus, are the neutrons. So it's right there in the name, neut. These are not positive, these are not negative. Neutrons have a neutral charge. They are also in the atomic nucleus right next to those protons, and you can't see it from looking at it, but they also have a mass of 1. So neutrons, neutral charge in the atomic nucleus, mass of 1 AMU, so they've got 1 just like protons have 1. So the neutrons don't impact what the element is. You know, you could be carbon with a certain number of neutrons, you add or remove neutrons, and it's still going to be carbon. It's carbon because of the number of protons. But you can have different numbers of neutrons. It's not going to affect the elemental properties, but it's going to cause something called isotopes. So here is carbon 12. It's got 6 protons, 6 neutrons. 6 plus 6 is 12. You see why it's called carbon 12. And here's what we call carbon 13. It's got 6 protons and 7 neutrons. Remember, neutrons have an atomic mass of 1, so adding an extra neutron is going to increase the mass by 1. This is carbon 13 because 6 plus 7 equals 13. And then there's carbon 14 with 8 neutrons. 6 plus 8 equals 14. All of these things are still carbon. You can still use them like carbon. They behave like carbon, but they do have slightly different properties. Again, we don't call these different elements. They're all carbon. We call these things with varying numbers of neutrons. We call these things isotopes. So atoms of the same element can have different numbers of neutrons. We call these things isotopes. So neutrons don't affect the element. They affect the isotope of that element. Okay, we got one more here. We know it's coming. It is the electrons. These are different in a couple of ways. So yeah, these have a negative electrical charge. They are not in the atomic nucleus. They orbit around the outside. And again, it's more accurate like this. They don't actually, orbit like planets around a star, but it's very convenient to draw them like this. And they have a mass of, well, it's not 1. I will annoy the physicists if I say it's 0, because it's technically not 0. But the mass of an electron is so incredibly tiny compared to the mass of protons and neutrons, we can basically ignore it. I mean, go back to this. It was carbon 12 because it had 6 protons, 6 neutrons. It didn't matter how many electrons were in here, probably 6, because they just don't impact the mass at all. The phrase that I like is that they lack functional mass. Again, it's not 0, but it's so small we don't care about it, in biology at least. So electrons, also known as E superscript minus. So this is a very common shorthand, not just for taking fast notes, but you will see throughout the quarter in a lot of figures and diagrams, the little E superscript minus sign, that means electron. So electrons, yes, they've got a negative electrical charge. They orbit around the atomic nucleus. And yeah, this phrase, they lack functional mass. So that does mean, if you're wanting to count these things up, the mass of an atom equals the number of protons it has plus the number of neutrons it has. Number of electrons don't really matter when it comes to this. And we saw this with carbon, just another kind of note here. Most elements have the same number of electrons as protons. We saw this in carbon. I guess it's hard to count the protons here because they're kind of overlapping one another. But we know carbon, based on the periodic table of the elements, boom. No, these numbers are kind of small to see. There's a 6 here. Carbon has 6 protons, and let's count them 1, 2, 3, 4, 5, 6. 6 electrons. I'm calling out the electrons and protons because these are the ones that contribute to the charge. There are exceptions, but many of the elements we are going to come across are going to have the same number of electrons as protons, the same amount of negative charge and positive charge, so they're going to cancel out, and this is not a charged atom. So most elements in biology have the same number of electrons as protons, giving them an overall neutral charge. Again, there are exceptions to this in the periodic table, but yeah, this is generally what we see in a lot of stuff that we care about in biology. Now, if you take a chemistry class, you will understand why the following statement is true, but in an introductory biology class, I don't want to get bogged down in the details here. I'm just going to make this statement, and trust me, there's a reason behind this, but trust me that this is true. Atoms are most stable when they have specific numbers of total electrons. Those magic numbers that we care about, not magic, but these special numbers, these particular numbers that we care about in biology are 210 and 18 total electrons. So like I just said, most elements have the same number of electrons as protons. So if we go back to this table here, helium, 2 protons and 2 electrons, it's stable, it's good. Neon, 10 protons, because it's atomic number 10, 10 electrons, it's stable. There's argon with 18 and so on. Yeah, these things are fine, but most other things are not. Most other elements here don't have, by default, 2, 10, or 18 total electrons, which means they're not as stable as they could be. So because these atoms are not as stable as they could be, they're going to do whatever they can to get to these total numbers. They are going to form chemical bonds with one another in order to achieve this stability. So this is the reason why chemical bonds are made, to get to these stable numbers. So the key terms define a chemical bond as an interaction between 2 or more of the same or different atoms that results in the formation of molecules. So yeah, I mentioned molecules in the last chapter. These are things that hold molecules together. So there are several types of chemical bonds. We'll talk about 3, starting with something called covalent bonds. These are probably the most common type of chemical bond that we're going to see in biology. A covalent bond, to, again, just read from the key terms, is a type of chemical bond, semicolon, forms when electrons are shared between atoms. So let's take a look at this. Here is a covalent bond between 2 hydrogen atoms. So a little bit of background. Hydrogen, by default, has 1 proton. Most of them have 0 neutrons. And 1 electron. So 1 is not one of those happy numbers of 2, 10, or 18. So this default hydrogen is really looking to get a second electron. Here's a hydrogen. Here's another hydrogen. And look what they've done. They've shared their electrons with one another. So again, this is one way of drawing this. Really, these 2 electrons are going to be sort of, moving back and forth between these 2 atoms in a cloud of probability around them. But yeah, each one of these contributes to each of these. So this hydrogen has 1, 2 electrons. It is stable. This hydrogen has 1, 2 electrons. It is also stable. These 2 electrons are being shared between the 2. You will see this written as a single dash, a single line between the 2 elements when you're writing out or seeing written out chemical compound structures. H, line H, indicating that there's a single covalent bond here. Now, this confuses a lot of students. It is called a single covalent bond, even though there are 2 electrons being shared, because as we're going to see, electrons are shared in pairs. So this is a single pair of electrons. That's why it's called a single covalent bond. And again, this is very strong. This is a close relationship between these 2 atoms. It's pretty difficult to break up these 2 H's. But again, it doesn't always have to be 1 pair. Sometimes it can be 2. Here's oxygen. It's got 1, 2, 3, 4, 5, 6, 7, 8. I guess we can go back to the periodic table. There's oxygen, atomic number 8. Again, I don't expect, don't memorize any of this. Don't memorize, how many protons boron has or any of this stuff. I'm going back to references, but by no means should you memorize anything on this periodic table. But yes, here's an oxygen. It's got 8 total electrons. That is not one of those stable numbers. It is pretty close to 10 though. It needs 2 more electrons to get there. And it can get there by sharing not 1 pair, but 2 pairs of electrons with another oxygen, for example. So now this oxygen has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's happy. This one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It is also happy. And again, there are 2 pairs being shared here. So this is a double covalent bond. And you'll see it drawn like this, the 2 lines between the 2 atoms. Now, there is a triple bond that can occur, which obviously shares 3 pairs with nitrogen here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Each one of these are stable. This is not very common in biological molecules, but I do want to call it out as existing. 3 lines here between the 2 atoms. But yeah, the triple bonds do exist. So these are all types of covalent bonds, which, yeah, I had earlier. This is very strong. A covalent bond is the strongest type of chemical bond that we're going to talk about. Electrons are shared in pairs. 1 pair, single covalent bond. 2 pairs, double covalent bond. 3 pairs, triple covalent bond. And I do want to point out all of these examples were the same element, like hydrogen sharing with hydrogen, oxygen sharing with oxygen, nitrogen sharing with nitrogen. It doesn't have to be that way. They don't have to be the same element. Here's an example of oxygen sharing electrons with hydrogen. So yeah, there is a single covalent bond here between the oxygen and the hydrogen. And this illustrates another thing. It doesn't always have to be just a single bond between 2 atoms. Sometimes atoms can have multiple partners, multiple bonds to different atoms. So yeah, here's this oxygen forming a single covalent bond with this hydrogen, and then another single covalent bond with this hydrogen here. So yeah, this is of course H2O, this is of course water, but yeah, this is just another example of this. 2 separate single covalent bonds, this one atom, a bond to this atom, bond to this atom, and they're different elements. So just more examples of this. Now, there's another thing that can happen in the quest for stability, trying to get to 2, 10, or 18 total electrons. Some atoms can achieve this stability by permanently gaining or losing an electron or 2. So before I read the rest of the slide, let's see an example of this. So here is sodium. By default, sodium has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons and 11 protons. 11. It's so close to 10. It would have to have, 7 more partners if it wanted to get to 18, but it's much closer to 10. The easiest way for sodium to get to its 10 stable electrons would be to just lose this 11th electron. So it gives away this 11th electron. It gets 10 total electrons. It's more stable this way. But now it's not balanced. Now it has 10 electrons, but it has 11 protons here in the nucleus. There's 1 more proton than electron, which is going to give it a +1 positive charge. Here's another example of sort of the opposite situation. Here's chlorine. By default, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 total electrons and 17 protons. That is very close to 18. And yes, it could try to form a single covalent bond with something like hydrogen to get to 18, but in such a big, bulky element, it's much easier for it to just get that 18th electron permanently. So this results in what is called a chloride ion. It's got 18 electrons, but again, it's unbalanced. Now it has 1 more electron than proton, so it has a negative charge. Remember, electrons are negatively charged. So this is not a bond. I'm working towards that, but so far this is just backstory to our second chemical bond. Some elements, some atoms permanently gaining or permanently losing an electron or sometimes 2. When this happens, they become an ion, which we saw that, but let me read the key terms definition here. An ion is an atom or chemical group that does not contain equal number of protons and electrons. So yeah, something that's charged. An ion is something that's charged, and it comes in 2 flavors, anions and cations. One of these is positive, one of these is negative. Which one is which? Well, to me, my dumb way of remembering which one is which, you see a little lowercase t here in cation. That lowercase t looks a lot like a plus sign to me. And if you remember that little visual clue, that'll tell you which one is which. An anion is reading from the key terms, a negative ion that's formed by an atom gaining one or more electrons, and a cation is a positive ion that is formed by an atom losing one or more electrons. So yeah, just some terminology here, anions or cations. So where's the chemical bond? Well, it is a fundamental force of the universe that positively charged things and negatively charged things are attracted to one another. So if you have cations and anions together, they will form what is called an ionic bond. Notice there's no sharing of electrons here. This is just the attraction between a positive atom and a negative atom. This is an ionic bond holding together sodium cation, chloride anion, forming good old sodium chloride or table salt. So this is the bond, the ionic bond. Key terms: a type of chemical bond that forms between ions with opposite charges. And they're not sharing, it's just this attraction between positive and negative. And I'm not going to put any numbers to how strong these things are, but it is worth pointing out that ionic bonds are weaker than covalent bonds. Again, covalent bonds, the sharing, that's the strongest thing that we'll talk about. Now, our third type of chemical bond is a little complicated. We need a little backstory to talk about this third one. So, a lot of text on this slide, sorry. Some elements don't play nice. So, before we look at this text, here. Some elements will share electrons, but they will not share evenly. Oxygen is one of these elements. So yeah, here is OH. We saw this a few slides ago in water. Here's oxygen, here's hydrogen. Here is a single covalent bond between the two. There are going to be two electrons that are being shared between these two atoms. But oxygen is an electron hog. It's greedy with its electrons. The technical term is it's electronegative. So even though there are two electrons being shared, they're not being shared equally. The oxygen is spending more time with these electrons. Remember, electrons are negatively charged. So if this atom is spending a disproportionate amount of time with negatively charged electrons, that's going to give it a negative charge. Not a full negative charge. It's not permanently gaining anything. They're still being shared. It is a partial negative charge. That's what the lowercase delta means. It has a partial negative charge. In contrast, the hydrogen is not getting an equal, its fair share of time with these negatively charged electrons. It is going to take on a partial positive charge. So let me summarize this. Some elements are more electronegative than others. Again, that's the technical term for being electron greedy. Oxygen is a very good example of this. In covalent bonds, these electronegative elements share electrons unequally. This results in what is called a polar covalent bond. So yeah, this is kind of going back to covalent bonds. This is a type of covalent bond. When they're not being shared equally, we call it polar. This creates partial charges in both of those atoms. And yep, in an OH, doesn't matter whether this OH is part of water or part of any other molecule. If you've got an OH as part of any sort of chemical compound, you're going to have this unequal electron sharing. The O is going to become partially negatively charged, and the hydrogen is going to become partially positively charged. Now, one other kind of side note here, it is possible for electrons to be shared unequally. It is also possible for electrons to be shared equally. So carbon is an example of an element that does play nice. Here's carbon and hydrogen together. And yeah, there's no charge here. There's no partial negative. There's no partial positive. They're being shared pretty equally between the two. So I just wanted to point out the terminology here. When electrons are shared equally, this is called a nonpolar covalent bond. And there's no charge or any of this stuff involved. CH, classic, fantastic, commonly occurring example of this. No charges in the carbon or hydrogen when you got CH partnered up together. So, okay. This is all backstory, because this is not a new type of bond. These are just, different types of covalent bonds. There's a new bond here that we call hydrogen bonds. Hydrogen bonds are attractions between the partial negatives and the partial positives in two different molecules or groups. So, again, fundamental force of the universe, positive is attracted to negative. That's true when we had full charges. That is still going to be true when we're dealing with these partial charges. Here's a partially positively charged hydrogen. It's partially positively charged because the oxygen it's partnered with is hogging the electrons. This partial positive is attracted to this partial negative in the water over here. This right here is the hydrogen bond. And I like this figure as well. It doesn't show the O's and the H's quite so clearly, but this is showing that, yeah, this right here, between this oxygen and this hydrogen, this is a covalent bond. 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 Covalent bonds hold these molecules together. The hydrogen bond is the interaction between these two separate molecules. Hydrogen of this H2O, oxygen of this H2O, there's the hydrogen bond. There's the hydrogen bond. As you could probably guess, this is the weakest of the three. It's definitely weaker than an ionic bond. This is a full positive and full negative. Obviously, partial positive, partial negative is going to be weaker. So hydrogen bonds, there is a key terms definition. I think we did a good job of walking through this, but if you want a summary of this, the key terms define a hydrogen bond as a type of chemical bond between slightly positively charged hydrogen atoms and slightly negatively charged atoms in other molecules. So the positive always has to be a hydrogen. That's why it's called a hydrogen bond. The negative thing is just whatever, just anything else that's negative. Usually it's an oxygen, but just anything else that's negative. That makes it a hydrogen bond. Common abbreviation is to call them H bonds. Hydrogen is H in the periodic table. So H bonds, hydrogen bonds, same thing. And yes, this is the weakest of the three. This is weaker than ionic bonds. We had covalent, strongest, ionic in the middle, and hydrogen bonds as the weakest of the three. Even though these are very weak, we're going to see in certain macromolecules thousands and millions of hydrogen bonds holding these things together. They're weak, but when there's a lot of them, they can do very impressive things. So in sort of grand summary here, all of these chemical bonds are important in holding together all of this stuff. Organic molecules, macromolecules, organelles, and cells, all these big structures are held together by these chemical bonds we've just talked about. Oh, and I think I've been throwing out this term, organic molecules. This is the first time I've highlighted it in the key terms. If you're curious, an organic molecule is defined as any molecule containing carbon except carbon dioxide. So we will see organic molecules in this chapter and the next chapter. Things like sugars are organic molecules, proteins are organic molecules. If you see their structures, anything with carbon except CO2 is defined as an organic molecule. So just keep that definition in mind here. All right. Let's finish up this recorded lecture by talking about water. So water is very important for life for a lot of different reasons. So water has partial charges, both negative and positive. And we saw this in this figure here. Any given H2O, the oxygens are all partial negative. The hydrogens are all partial positive. So if you're talking about, a cup of water or a puddle of water or whatever it is, that whole thing has a bunch of positive charges and a bunch of negative charges. This means water is really great at interacting with anything else that is charged. Take a look at this. So we all know that salt dissolves in water, and here's why. So here's the negatively charged chloride ion. Yes, it was happily ionically bonded with the sodium full positive charge, but when it's in water, it gets to be fully surrounded In 3 dimensions, by the way, we're looking at a flat image here, but in 3 dimensions, this chloride ion gets to be surrounded by the partial positive charged hydrogen. And sodium gets a similar treatment, surrounded by the partial negatively charged oxygen. Here's something else we know dissolves in water. Sugar dissolves in water. And here's why. Look at this sugar molecule. Don't memorize this, but look at all these OHs. Remember what happens. Every time you've got an OH, whether it's part of water or anything else, anytime there is an OH, maybe I should show this. Anytime there's an OH, the O is going to be partial negative, the H is going to be partial positive. Well, if sugar is in water, all those partial positive H's get to be with partial negative O's on molecules of H2O, 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 just fully surrounded in 3 dimensions. This is why water is great at dissolving stuff. Anything charged, whether it's partially charged like this sugar, fully charged like this salt, it's going to love being in water because it gets to be surrounded by its opposite charges. So in summary, because of those partial charges in water, it interacts with, it dissolves anything else that is charged. So there's a term for this. We call these things that love being in water, we call these things hydrophilic. So anything that's charged, we call hydrophilic. Hydrophilic atoms and molecules will dissolve in water. Sodium chloride, glucose, great examples of this. In contrast, if something is not charged, it doesn't want anything to do with water. We call these things hydrophobic. Philos means love, phobia means fear, obviously hydro means water. So yeah, hydrophilic means water loving, hydrophobic means water fearing. Atoms and molecules that are hydrophobic do not dissolve in water. And yeah, oil, great example of this. Pour some oil on top of some water, it's not going to dissolve. It's going to clump together with itself. If we look at the chemical structure of fats and oil, which we will in later chapters, you'll see that they're not charged at all. So yeah, they don't want anything to do with water. We call these things hydrophobic. Now, there's a reason why when astronomers, going far afield for this explanation here, but there's a reason why astronomers look for water on other planets and moons when they're looking for life. Water has so many properties that are convenient for life that it's hard to imagine life existing and being sustainable in the absence of H2O, in the absence of water. So just listing out here some of these properties of water that are convenient for life. One of these, water is a very effective solvent. So what is a solvent? Well, we've already seen a solvent in action. A solvent is just something that dissolves things. If I can read from the key terms here, a solvent is a substance capable of dissolving another substance. And again, because of all these charges, water is fantastic at this. And again, just for perspective, we're comparing water to other liquids that you would find on other planets and moons and things like that, compared to liquid ammonia or ethanol or acetone or other stuff like that. Water is great at dissolving things. Fantastic solvent. Another property of water that's very nice is that water is sticky. And again, we don't normally think of water being sticky. We think of, honey or syrup as being sticky. But again, if you're comparing H2O to ethanol, acetone, liquid methane, liquid ammonia, whatever, it is very sticky. Water absolutely sticks to itself. We see this phenomenon with, raindrops, drops of water. This will not happen with ethanol. It's so sticky, and we know exactly why it's sticky as well. Water loves to stick to itself because every single H2O is going to be hydrogen bonding with all the other H2Os that it can find surrounding it. Water loves itself. Water loves to stick to itself. We call this property cohesion. The key terms define cohesion as cohesion's actually not in the key terms. Cohesion just means that it sticks to itself. It's my mistake here. Surface tension, however, is in the key terms. Surface tension is what happens when water would rather stick to itself than break. So because water loves sticking to itself so much, you can actually apply some amount of force to this water and not break the surface of this. It would rather stick to itself. Surface tension, reading from the key terms here. Again, sorry about this. Dynamically changing. No cohesion. It's just water sticking to itself. Surface tension is tension at the surface of a body of liquid that prevents the molecules from separating. So yeah, very convenient for certain organisms. So water sticks to itself. Water also sticks to other things. So that is what we call adhesion. Again, my bad, not in the key terms. Adhesion is just water sticking to other things, and this results in capillary action. So we can see water sticking to other things if we shove a narrow tube in a beaker of water. And because water loves to stick to other stuff, just like it loves to stick to itself, this water will, fighting against the force of gravity, climb up the wall of this tube. And this seems like a fun science experiment that doesn't really seem relevant to life. Actually, this so-called capillary action of water climbing up the walls of a thin tube because it wants to stick to the walls of that tube is incredibly important for plants. This is a very important aspect in how plants transport water from their roots all the way up to their leaves. So again, adhesion is just water sticking to other things. Capillary action, reading from the key terms, this is something that occurs because water molecules are attracted to charges on the inner surfaces of narrow tubular structures, such as glass tubes, drawing the water molecules to the sides of the tubes. So again, very important for plants. Now, there's another important property of water, and that is the fact that water ionizes. So we know what an ion is. We defined that earlier. It's something with a full positive charge, full negative charge. And this is something that water just does on its own. You got H2O, water. It can break apart into OH minus and H plus. So if you're sipping on a glass of water, most of that is H2O, but within that water, within any cup or puddle or whatever of water, there's going to be some amount of OH minus, which is called a hydroxide ion and negatively charged, and there's going to be some amount of H plus in there as well. A hydrogen ion, also known as a proton. So if I can zip back way far back to the beginning near the beginning of this chapter, by default, most hydrogens don't have any neutrons. They just have a proton, one proton and one electron. So as it turns out, if you take away that electron, it's just one proton. So yeah, H plus, this hydrogen ion, is also just a proton with 0 neutrons, and it's lost its electron. So yeah, water ionizes. It does this thing. It breaks apart into these two ions. This is incredibly convenient and important for life because we use these ions a lot. We'll see this throughout the quarter, especially this H+. The fact that there's just some of this floating around in the cell, in the environment, is going to be very important. We're going to see a lot of chemical reactions that make use of these, and this is convenient because water just makes these. There's always going to be some of these around in water. I'm just going to say, in summary, these ions, hydroxide and hydrogen, are used in many chemical reactions in the cell. Okay, so there's a little bit more about water to talk about, but this is typically where I run out of time on things in person. So we'll finish up this chapter in the next recording. This is the end of recorded lecture 1-2.